where we're going with this, this idea of equilibrium and existence. It also kind of helps to slot in the example of a dynamical system where choices are being made into some of the traditional tools, which are always still of value, things like game theoretic analysis, to say, okay, what would happen in this situation? We're going to try to do a little bit of a compare and a contrast on the perspectives that a GDS representation has in comparison to such a strategic based or strategic facing equilibrium analysis. So the idea, just in the one slide summary of the crosswalk problem, was this idea that we have this location for which individuals would like to cross a one-dimensional line. They have to select a point on the line that has potentially various trade-offs in terms of their benefits, and we'll get more specific on this, especially in the game theory side of things. And then there's a decision-making body, a government, that actually has to decide where to place a particular focal point or a particular coordination activity, in this case, the crosswalk, so that the drivers and the pedestrians can reach some sort of a conclusion. And the idea we went through last time was to formulate this specifically as a GDS, where we broke out the state transition of traffic flow away from the decision-making on the part of the pedestrian, just to look at what would happen in the environment of the pedestrian making a decision on the basis of a crosswalk that's already present. And so there's a system of traffic flow, which we have as the state xt. We had decision-making on the part of the pedestrian, whether or not to cross, that was S. The location, if they choose to cross, that was P. The crosswalk location then is set at some point K, and we're going to get into more descriptions on kind of how that we derive that K or choose that K. And finally, there's some sort of ability for the world to shape things that we can't necessarily control, although we can measure and perhaps model, that we just formalized as luck. And then with that, we have this idea that if you were to actually stand on the corner and just watch things and write down transitions and watch how people make decisions and then watch the outcomes and how they change over time, that you could create just by virtue of the fact that you can visualize what's actually occurring, a transition from one state or one set of states to the next. So we have a partition of the different states where we're using the idea that a positive value is traffic flow for xt, 0 is when traffic has stopped, and less than 0 is when cars are being turned away as an accident. And then we have transition probabilities from one state to the next. And I'll just mention very quickly on this slide that there's a correction here. I dropped a 1 minus S term. It should be multiplying the epsilon. So for those of you who are looking through the notes, wondering why that last row was adding up to sometimes greater than 1, that was why. So just a small note to mention that essentially, and that was sort of the question I left at the last time, that to drive home the idea that, hey, there are things that are happening outside of the control of the system. So if an individual chooses not to cross the street, if S is equal to 0, for example, then you end up with this possibility that there still may actually be an accident, for example. So just to build this as a way of saying there's measurement and a way you can intuit what's happening from what's going on, provided that you know what can occur. And in an environment like where somebody is crossing the street, you can actually see where they're crossing. You may not know where their ideal point is. You may not know why they're crossing at a particular location or how they've chosen things. But conditional on observing the actions, you're able to build how the system moves from one state to the next. And that's why this separation in GDS from the procedure or the algorithm, the automation that is occurring as the state transition occurs, conditional upon what decision-making is done from the decision-making automation, that distinction helps a lot to ensure that you can make that type of movement. Negative flow, again, is just a shorthand that we had as the idea of an accident having occurred. The police are coming and they're turning traffic away. So down this one-way street, cars that are turning in are backing up to get out of the way because that road is now blocked. So that's the idea for this sort of very, very oversimplified environment on this single dimensional line. Okay. Now, we can take this one step further and say, okay, I can observe all of this and I can see the transitions that are occurring, but I'd kind of like to understand what's going to happen. And of course, if we're designing a system, then we really want to be able to say, okay, conditional upon what stakeholders would like or what clients would like or what we think the system should behave as, we want to know kind of what are the effects of making different changes when we're designing the system. And broadly speaking, we can look at two different kinds of solution or solution concepts. One of them says, okay, I've got this system, I've got this structure, what's going to happen? What's my expectation of what the outcome is that is going to occur conditional upon certain facets or assumptions or ideas about what the system is doing. The other one says, well, given the structure of the system, what I care about here are what the possible actions are. And the possible actions then lead to possible outcomes. And so I'm not actually considered more or less what's saying, let me focus on a particular kind of behavior. Instead, I'm saying there's a whole suite of possible choices. And conditional upon that set of choices, there are a set of trajectories that move onward. And so just from the question from Chris regarding actions, there are indeed dynamic controls that can occur. You could put in an individual that is essentially a robot that is looking at the state and conditioning upon it with a particular action. Or you can think of an agent as an individual that is already assimilating state-based information and conditioning on an action. So the idea of having a dynamic control or a state-dependent control is something that's a natural fit for the agents as well as for other processes. So the first particular kind of expected outcome solution is what we might term an equilibrium, where the notion is that we're actually seeing something such that if we were then to look away and look back again, we'd sort of see the same outcome because it's the expected outcome. And maybe that has some sort of dispersion because of randomness, but overall we can define a particular reduced form statistic such that we call this the expected value or the expected outcome. And this is answering a question for us. It's answering the question of, well, given the system and the specification of the behaviors of the participants, what is it that's occurring? Now, the second type of question, the idea of the possible outcomes, the idea of reachability, what might occur, is a different sort of question. This is really about looking at the things that admissible actions allow. And so we could phrase this as given a trajectory of states, so things that we see happening over time, does there actually exist a sequence of external actions, these actions that decision makers are making plus realizations from randomness like luck, such that starting from an initial condition, you can get that trajectory to be generated. So it's still an existence question because you're saying, does there exist a sequence of external actions? But you can see in this case, what we're saying is that there's a whole spectrum of possible solution trajectories or trajectories of states. And then we're asking for support for each one. And we're doing so agnostic at that point as to what kinds of behaviors are being ascribed to the participants. It's a little bit of a nuanced distinction. And the reason it's important is because we have lots of other tools to take a dynamical system and solve for an equilibrium. If we have a differential equation where the rate of change of a variable over time is a function of its value, for example, we look naturally at the point where that rate of change is equal to 0, and that particular value is unchanging. So we have these ideas that there is something nifty about an equilibrium. And so we would like to understand how much structure we need to place upon a dynamical system like this to be able to ascribe this first solution concept and the second solution concept. And so a motivating example for understanding that first equilibrium concept would be to apply the tools under which we specify the entire environment that individuals are conditioning on, and then run the system forward to see what the outcome is. And a game theoretic representation helps a lot to be able to do that. So recall that in game theory, we specify 3 different types of fundamentals or primitives to the system: the players, the strategies that they adopt, or the action space over which they choose strategies, and payoffs. In our environment for the example, the pedestrian is a player in this game, and they decide whether and where to cross the street. And depending upon what they see and what they condition on and what the behavioral assumptions are, that selects the strategy that they have over what they see and then what they decide to do. Now, we're going to couch this in the idea of moving from an environment where we simply say there exists a crosswalk in a particular location to one in which there is a second player in this environment who's selecting the crosswalk location. So that's that representative government or a decentralized group of activists or individuals who say, look, we need to put a crosswalk here, but we recognize the fact that there are pedestrians who are going to use that and they have a certain behavior, and perhaps conditional upon that, then we decide which location the crosswalk should be placed at. So we have a second player, which is the decision-making process, and then the crosswalk location, conditional upon the information at their disposal, is their strategy. And finally, conditional upon that location and the pedestrian's crossing decision, there exists a traffic outcome. And we have that partition where we have accident or traffic jam or traffic flow. It could be as fine-grained as is necessary for the specification, but in any event, there's a an outcome that is determined by how the players play their strategies, and then there's a payoff. And that payoff then dictates for individuals whether or not this was the best selection of strategies conditional on others, and whether there is a way in which we can find, to a certain extent, a focal point such that a deviation from one particular strategy leads someone to be strictly worse off, conditional upon that other individual choosing their strategy. So the game theoretic specification is something that completes the selection process from the admissible action set. So when you're using game theory, you're going to say, here's the admissible action set, and now here's some apparatus that allows this system, to this individual, to select, conditional upon the state of the system perhaps, from that admissible action set. So let's look at these types of behavioral assumptions. And this is essentially for, again, this is for exposition. This is not the specification of preferences. What we're doing is saying, okay, if we want to really want to get an idea of what equilibrium should look like from a game theoretic point of view, what's the machinery that we want to have available to select from the admissible action set? And in this case, it's the selection for some kind of preferences. So how people make decisions, the thing that we can't see when we're sitting on the corner watching what's happening. So here's some example assumptions for the pedestrian as a player. First, we might say that there's existing a benefit from arriving at the game store, that there's a place which they want to go, that ideal point from the first lecture from 2 weeks ago. Also, that there exists a cost to crossing anywhere other than an ideal point. We call that a disutility from the parlance of this decision-making of an effort that they're trying to make. If they move away from their ideal point, they suffer a loss. And finally, there's a default benefit from not crossing at all, so that they're maybe not so happy that they can't cross to the other side, but they get some derived benefit from remaining on the far side of the street, their opportunity cost. And from this, you can create an expected payoff, some sort of sum between the benefit and disutility, where the disutility is negative. And it's conditional upon what actions are available to that particular individual, whether or not to cross, where to cross, what the traffic outcome eventually is, which is the associated payoff to the individual, and how luck affects the outcome. And notice that final step on payoffs, you're actually specifying a mapping between the outcome of the state and what happens to the player. So in the case of an accident, there's an injury. In the case of the traffic being stopped, perhaps there's some sort of qualification that occurs for the individual who's crossing, where people are yelling as they're crossing the street. These are the things that map from the output state to the benefit or the cost that's being associated to the player. Okay, so in a nutshell, then the pedestrian's game, and this kind of rehashes what we had seen before, but now placing it within the context of how these preferences are being set up. And this is an environment where here I've placed a crosswalk at a particular location, but that may not necessarily be true. It may just be that there is a particular idea of where they want to go relative to this ideal point, capital I, and that decision S on whether or not to cross the street. So they would ideally perhaps like to move there. Any other point P gives them a disutility. And of course, there may even be a much larger disutility for having to walk all the way to the crosswalk and cross over, bearing in mind that there's a particular payoff for the outcome of the traffic flow that might also accrue as a benefit for that decision that's being made. And across this entire tapestry of the decision-making from the point of view of the individual is luck blowing in and doing something, causing someone to trip, causing brakes to fail, causing issues to occur that are outside of the control of the player themselves. So these things are all part of the system that allows us to specify, conditional upon that game structure, the preferences of, or the way in which the player as a pedestrian is choosing from the admissible action set, the line that we have for the street. Okay. Now we've added in the decision maker into the problem now. And so what we're looking for here is how the crosswalk decision maker sets up their own understanding of the system, conditional upon what they would like to see. So we would describe to the decision maker a reason for placing your crosswalk. So we'd say, hey, there's some kind of a benefit to the decision-making collective or representative government from placing the crosswalk. And we could say, well, okay, there's a preference ordering. They would prefer to have traffic flow, which is something they would prefer to have over a traffic jam, which is something they would definitely prefer to have over, say, an accident. So we say, okay, there's a preference ordering. Maybe it's intuitive, maybe it isn't, but we decide that this is the way in which we're going to model the way that they are deciding from their choice set. And of course, what they need to be sure of, what they need to be sure of is that they are examining the actual cost of the implementation of this particular piece of what is essentially civil infrastructure. So there's a cost associated with the crosswalk. It may be location dependent. There may be areas on the street which are cheaper than others, but that has to be balanced across according to the probability or the expected likelihood, the expected payoff of placing a crosswalk in a certain location and then getting something along the lines of the best that they can get for their preferences. So an expected payoff here, which is now a benefit minus a cost, is then conditional upon that choice that they're making, where to place the crosswalk. Conditional upon that, then you have the pedestrian's behavior. That then leads to a traffic outcome. And lurking behind all of that is the expense and what they have to eventually raise in terms of funding and where they go from there. Question in the chat. Is in this context, the order of making the decisions important to the outcome of the game? Yeah, it's a decision-making issue that if you made it as we are here, for example, environment where the crosswalk decision is placed first, then that can be different from a simultaneous move game. The closest analog you would find from something like industrial organization or monopolistic competition would be simultaneous moves between firms versus a Stackelberg equilibrium where there's an incumbent moving first and then there's a respondent. So there is definitely a difference. Okay, one slide snapshot of what the decision maker's game is. That's simply to place the crosswalk at different locations with a particular cost associated with this. Very simple. So the question we want to ask is, all right, well, what equilibrium concept will we adopt? Straightforward one, the one that we kind of go to when we first look for game theoretic equilibria is a Nash equilibrium. A Nash equilibrium is an equilibrium such that conditional upon everyone playing the Nash equilibrium, unilateral deviations from Nash are not optimal. You would prefer, if everyone else is doing Nash, to also do Nash. And what helps in the formalization of this and writing out the actual order of what occurs and the equilibrium that occurs, you can actually refer to a similar environment, not the same, because that has to do more with product differentiation. But the Hotelling linear city model has a lot of flavor. It's a 1D environment where you're also trying to place things with a particular landscape of preferences. So you can actually build some of the same cost-benefit analysis. And that means that if you're taking this expression of the preferences, of the behavior seriously, that on the margin, the pedestrian is going to choose where to cross so that an expectation, the loss from an accident, and perhaps from stop traffic, is just offset by the gain from crossing nearer to their ideal point. So that marginal cost equals marginal benefit. And this, whether or not people recognize it or not when they're just choosing a point to cross the street, is this idea that regardless of whether or not you assume that somebody is literally writing down the mathematical formalism, taking derivatives, and then figuring out their optimal location, or if they just cross the street and behave as if they've done all of those things, game theory doesn't tell you anything about it. So it won't give you the expression of whether or not people are actually doing something or whether or not their representation is doing something. They're doing something as if these things are occurring. But in order to get predictability, and to ensure that we have some kind of a content which is not vacuous from ascribing benefits and costs, there has to be some trade-off. At the same time, we have the crosswalk selection by the governance process or the decision-making process. There's some sort of a vote that goes on, or there's some sort of debate that happens. And what they are attempting to do is also to find an optimal where they're getting the expected benefit over the cost, maybe minimizing the probability of an accident or maximizing traffic flow, are impinging upon that benefit, that preference ordering. And in this framework, and it's also getting back to Chris's earlier question, this framework is important to be able to distinguish what people know versus what they don't know. What we've said here is that a simple environment to get a simple series of outcomes would be to say there's complete information, which is that you can see and understand what individuals can choose, so that everybody who's watching the decision-making process knows how the crosswalk decision is being made. And on the other hand, the decision makers are actually understanding what it is that each pedestrian is actually doing when they're making their decision on whether or not to cross the street. So these are all things that can be relaxed, and you can get different types of equilibria or sets of equilibria that may occur. In the simple case with complete information, in a repeated game environment, it's not too hard to show that it's possible that no one uses a crosswalk. The crosswalk is placed in a particular location, but that location itself is actually not a place that anybody uses. And that's because their idiosyncratic decision-making has concluded that for them, it's worth crossing better closer to their ideal point because the probability of an accident is low. And so we all know environments in which we have perhaps sparsely populated roads or roads that aren't traveled very often, which has a crosswalk, and yet nobody uses it. But there are more equilibria. So there are, in fact, one of the things about Nash equilibria is that there are often many, many of them. Another one is a focal point equilibrium or a Schelling point equilibrium. This also exists where people focus upon the crosswalk location because in their particular environment, it actually helps them to understand the predictability of traffic flow. And that then impacts the probability of having an accident. And so even though the cost of going to the crosswalk may be larger because they have to walk away from their ideal point, it affects the probability of them getting involved in an accident. Now, it's nice to have an equilibrium like that. It's the one that we kind of think should be the best one in the sense that then we have a coordinating mechanism that hopefully reduces, if we're using as our objective, minimizes the probability of an accident occurring. But it's not stable in the sense that you can cross next to the crosswalk, but it's kind of close enough, or a kitty corner from the crosswalk, the actual jaywalking from diagonal to diagonal, that's also close enough. There are lots of behaviors that sort of small first order perturbations away from the crosswalk location that are near enough that you still get, let's say, focalness without actually using the crosswalk itself. But there are other ways in which you can try to refine this. You can try to tighten it down. You can add norms and constraints. You can add laws, making it illegal to cross at any other location than a crosswalk, and just add more probabilities of negative outcomes, not just accident, but also getting caught by an authority who then fines you for not using the crosswalk. But in the end, you get this first kind of existence of an equilibrium, this notion that conditional upon understanding how individuals choose from an admissible action set, you can say a lot or a little about what is actually occurring in their environment. Okay. Any questions before we move to the GDS representation version of that second part of the question? Okay, well, hopefully straightforward. If you haven't seen the game theory before, hopefully at least the intuition about how people are making choices and how they condition upon those choices was clear. The concept of the Nash equilibrium itself it's the strongest, weakest equilibrium notion that can be used. There is a lot of literature on expanding it and broadening it, but it all relies upon the notion of some kind of decision-making algorithm that's being assumed for individuals. And they can sometimes make mistakes. You have trembling hand equilibria where people are wanting to pull lever A, but actually pull lever B by accident. Somebody wants to cross at that location, but slips and crosses at a different location. Many different extensions to this, but they all kind of revolve around that ability to kind of package the behavior and then the decision, the choice from the admissible action set. Now, you may be thinking, okay, we've got this GDS representation. Do we really need it to be able to do something like an equilibrium? After all, we constructed explicitly this representation using an a priori partition of the state space. And so the question then becomes, well, within this context, do we have enough information to really give us the power, sort of that seductive power of the Nash equilibrium to tell us what's actually going to happen? In other words, do we also have an environment which affords restrictions on the system's state trajectories imposed by decision-making behavior? If we have no such restrictions from behavior, if we're just saying, look, it's just an admissible action set, well, then to a certain extent, our hands are tied. We have to say, okay, admissibility alone is going to dictate what the reachable equilibrium trajectories are. We can't select further from within those without bringing on board the different behaviors of selecting within an admissible action set. So the reachable states of the system then are those that are reflected only by the restrictions of admissibility. It's only that part of the set that says, this is what you can choose from, and this is what you cannot choose from, that tells you what might be possible in the future. And this means that we relax a little bit the idea of what we consider to be the thing that will happen next. And so we move from an idea of having an equilibrium to something that gives us the idea about how to look at the state space as places where we would expect, if we were just to look away and look back, we'd expect to see the system somehow nearby, in quotations. And the notion that the trajectories themselves, even though we've left admissibility as an open set, there are places that those trajectories somehow collect and sit around. Now, we know in the way in which we've described the system that conditional upon things like the crosswalk's location or on the exogenous chance of an accident, that some of the subsets, that this partition that we made for the traffic flow, end up being more likely than others. And this is coming out simply from the way in which that Markov transition matrix moves from current states to future states. So we can build then this likelihood of unimpeded traffic. We could say, well, there's this chance, there's a trajectories that seem to be around this notion of having traffic flow being positive, xt greater than 0. Maybe there's a way in which we can model that ability to get to that part of the state space, for example, in the Markov transition matrix, and then choose a point k star for the crosswalk that maximizes the chance of being in that part of the state space. So from the point of view of the decision-making body, that governance process saying, how do we vote on where the crosswalk is, what they may be looking for is a way to say, conditional upon where that crosswalk location is, for a given set of initial conditions, I will arrive at a reachable state within the set of locations that say maximizes traffic flow or say minimizes the probability of an accident. And this is called controllability. It's not controllability in the Big Brother sense, it's controllability in the sense that there exists an initial condition that will give you a likely outcome that you are looking for. And what you're looking for in that case is then contextualizing the different hotspots that will occur in the state space on the basis of the admissible action set. And whether or not there exist sequences from that admissible action set that, conditional on the initial conditions, will get you to those states. If you can figure out a behavioral model that then supports those sequences of choices from the admissible action set, well, so much the better. Then you could say this particular kind of environment would be incentivized by behavior of these individuals. So we would say, given a particular mechanism, these individuals would look at the menu of admissible actions and say, well, I kind of choose those, or I would be likely to choose those. And that would put me in the reachable set of the trajectories that I'm looking for. Okay, so there's a little bit of a difference here between those two types of equilibrium notions. And the driving force in GDS is about representation. It's about how you can represent the choices that are made from the admissible action set to support solution trajectories that you're interested in. Okay. Now, from this point, we have the machinery in GDS to discuss the existence of state trajectories by imposing these different behavioral assumptions on decision-making. So it's not a requirement at this stage to go in and look at how would behavior change on the basis of how individuals move, but rather, given the fact that we know there may be supporting particular reachable states, sequences of choices from admissible action sets, in what context can we build decision-making that allows us to conclude that these particular types of movements are allowed? So as an example, if we want to look at focal point seeking as a behavior, if we say individuals are looking for a way in which everyone kind of agrees on what to do, well, then we can recover the Nash equilibrium. If we look at cost minimization as our driving goal, this idea that we want to get across the street to get to our gaming store at all costs, then we can recover an anything goes style equilibrium. Another one is a social norm, or a way in which we say, hey, you have to go there with a fine or a penalty in case you actually are crossing at the wrong location. Or if you have some sort of shaming of somebody where people kind of tisk you as you are crossing the street or jaywalking in a different location. then you can recover the crosswalk as a collective good. So the decision-making process itself allows for the governance decision that is being done to be conducted on behalf of the society as a whole. But each of these are allowed within the context of selecting from that admissible action set. And as a result, each behavioral assumption acts as a constraint on the resulting state trajectories to be one or another of these hotspots in these reachable sets. And it's important to think about that as a constraint, because formally, from the point of view of just how the math would work, what you are doing is you are constraining the system such that you are asking the question, is it possible to build such a constraint set such that eventually I'm going to have decision-making that will support that constraint set? Sorry, just a second. Oh, very good. Kids are off. Okay, so hopefully that part of this has made sense. It's a little more abstract than what we've seen from the Nash equilibrium side of things. But the question here is, are we able then to claim with a GDS representation that there are selections from within the admissible action set that get us where we want to go? If the answer is yes, then we can say, great, the GDS representation is giving us the ability to look at reachability, the reachable hotspots in the state space, as the things that may be likely to occur. On the other hand, it may be, because we haven't discussed this yet, that even though we have a GDS representation, that the pieces that we've put together are not compatible with each other enough to be able to recover those choices from the admissible action set. And so in the paper, Zargham and I have some sufficient conditions for when a GDS representation exists within this context. In other words, going back to that original question, so that we can find points in the admissible action set that support a solution trajectory that we're looking for from a set of initial conditions. Now, this relies upon two main things. And really, these two main things are, in a way, the first one is like, if you don't remember anything else about this, this is the thing to take home, that you need in GDS a clear separation of the system state and its transition from external impacts like decision-making, like randomness, and so on. So that's that distinction between procedural automation and decision-making automation. So you need that distinction to be clear, and it needs to be something that you can rely upon in the representation. The second restriction, which is more or less a restriction on behavior, it kind of rules out very odd behavior or anomalous types of behavior, but not necessarily something that you would say might not exist or might exist, but it tells you whether or not the conditions are sufficient, is a technical consideration on decision-making as a constraint. And in particular, it relies upon and strongly upon convexity. And so for those of you who remember what convexity is, it's the fact that you can always, if you have 2 points in a set, you draw a line between them, then what's in the line is also in the set. But there are no holes in the set such that you cross over this giant valley and you can't make yourself stay inside the set by moving across. So as long as the way in which decision-making is performed does not have these types of holes, let's say, then the sufficient conditions also hold. Okay. There's a lot of math fudging going on here that we're not going to get into. So what I'll do instead is kind of create for you an environment. This is just one offshoot of the crosswalk example. We're going to modify it just slightly to make it, let's say, impossible, in quotes, to represent as a GDS. And this hopefully will give a nice contrapositive to this existence question so that you don't leave thinking, on the one hand, hey, GDS can do everything. Why do I need Nash equilibrium? Why do I need game theory? Or on the other hand, oh, it just can't happen because the example that you've created is rigged so that GDS works. So just to give you an example of how this changes, let's modify the crosswalk problem slightly and change it in one particular way. So here again, we have the road, we have the gaming store, we have traffic flow through the automobiles. And you'll notice what's been added here is a driver of the vehicle. That guy parks in the middle of the one-way street. We've all been here before. You're driving along, somebody just stops, the hazard lights goes on. They get out of their car, the car is sitting there blocking traffic, and they cross the street, run into the store. Okay. So this is the modified crosswalk problem. You still have a pedestrian, you still have traffic flow, and you still have the location potentially of a crosswalk. But what's interesting is you have a reversal of the cause and effect of what you had in the previous environment, because traffic flow stopped before a pedestrian crossed. And the reason for that is in this particular environment is not because the driver saw a pedestrian waiting on the crosswalk and had by law to let them go or wanted to let them go as a focal point, but rather it was because there is actually an extension of roles, as the pedestrian can also be a driver. And that means that in this modified example, the context is determining the role when you're watching from the outside. If you were sitting on the corner, again, trying to build your Markov matrices, all of a sudden you're watching individuals who were not pedestrians more or less appear and then act in the pedestrian role. And then perhaps 5 minutes later, come back out of the store and then assume the driver role. And this is the crux of where we kind of we're bending and bending now the GDS representation until it breaks. This is the idea where the role itself is being selected by a decision maker. So the procedural automation example that we've had for the crosswalk has been the driving of the vehicle. And we have the decision-making automation of the individual acting as a pedestrian and choosing where to cross. That was the first part. But in this modified example, we've added something else, and it's here in red. We actually have a decision maker deciding on the role of whether or not they are a part of the procedural or part of the decision-making automation. And a system where a decision maker can decide whether or not to be part of the state transition or the input, and I put in quotes here, cannot be modeled as a GDS. Now, why is this? What's happening here? What's actually going on underlying all of this? Remember, we have relationships in the state transitions versus the admissible action sets and the G functions that we have for behaviors, where individuals see the state of the world and choose from the admissible action set. And the way that they do that is represented in some sense by a function. So formally, what's happening here is that we're taking the state transition function, the procedural automation F, which says, given the current state and an action and a set of parameters, what's the future state? That this cannot be composed with a selection from the admissible action set represented by a function G. So you can't substitute in for U in F of X, U, and K, this function G of X, which you could before if you had specified it as a completely separate roles between the pedestrian and the driver. And the reason for this is that the state transition itself now functionally depends upon G, not just on the outcome, but actually upon how that role is decided between being a driver and a pedestrian. So that F is not simply F of the state X, the action chosen U, and a set of parameters K, but is now actually functionally dependent also on the function for decision-making for the decision-making automation, the G of X. And this breaks the GDS representation. It violates the sufficiency conditions regarding the existence of the GDS that can generate the reachable state trajectories. Now, it may be clear as to why it breaks GDS, may be unclear a little bit, because in a sense, functional dependence and composability may be kind of something that we can recover by doing some sort of nice functional derivative of some sort, and then saying, okay, this is how it changes. But just to say that the sufficient conditions, as in the paper, as we understand the GDS framework at the moment, doesn't support the ability to have that functional dependence. So the sufficient conditions are not necessary conditions. So there may still exist a GDS out there that allows this functional dependence and still allows that separation between the way the state moves along and the way that the individuals are making their decisions. But it may look very different from this simple example that we've created in the crosswalk environment. And so the way that the GDS representation of the modified crosswalk example would look probably would look vastly different from the simple Markov state transition that we've used in the current analysis. Okay, so hopefully that's helped kind of cast, let's say, a juxtaposition of where it is that GDS representation may fail by just tweaking the crosswalk example a little bit. And part, again, of the conversation that Chris and I were having earlier about whether this example kind of is is strong enough or has the legs enough to kind of move forward and use as one of the ways to understand what GDS does in terms of prediction, in terms of reachability and so on. This crosswalk example does afford the ability to kind of tweak it in different locations and come up with a very rich characterization of other behaviors without necessarily requiring a lot of other information that we would perhaps need if we were to be using an example from automated market makers or for example, from insurance or so on. So it's just on that, hopefully on that razor's edge where you can go back, think about it and go, oh, okay, so that small tweak kind of changed the rules of the game in which GDS can operate, but maybe there's a way I could sort of, I don't know what to call it, unfold the tapestry of possibilities on how I define a role, move up one level, and maybe reintroduce something like it. But in that case, it would not be fulfilling those sufficiency conditions as we currently have them. Okay. Any questions before I wrap up? We'll have some time for discussion before I have to jump off. But
quick one about this last bit. I can see sort of two ways that the pedestrian and the driver can become muddied, the roles. One is, I think you said that the pedestrian is a pedestrian, but prior to becoming a pedestrian, parked their car somewhere and started walking. And then when they go to the store, they go back into their car and now drive across the street. So they play both roles. The other one is what is it similar if the state or the jurisdiction of the crosswalk passes a law that says that all drivers must stop if a pedestrian is in the crosswalk? Does then the pedestrian sort of take on the driver role, because as soon as they step into the crosswalk, they've effectively braked all the cars coming up?
Yeah, that's a good question. So the way in which the GDS representation would provide the separation in the second case is by allowing the traffic flow to depend upon the state of the action that's taken. And so the action that's taken here gets expanded for the pedestrian to, I'm going to stand at the crosswalk and wait. And conditional upon that, then you have another state transition where the traffic then stops on the basis of the fact that there is behind the scenes perhaps a norm or a focal point that says, oh, I better do this, otherwise I'm breaking the law. So there you can still recover the separation between the two, because it isn't that the pedestrian is assuming the role of traffic flow or is acting as a traffic light, for example, as Chris was mentioning in one of the earlier comments, but rather that they've expanded the admissible action set to now include things like waiting at the light, because the structure of the system has a law that says when someone is waiting at the light, you must stop.
Oh, okay.
I hope that's it. Does that?
Yep.
Yeah.
Thank you.
Yeah. So it's actually not terribly well. I mean, I will defer to you guys. It may be terribly easy to come up with ways that break GDS. This was one of the ones that I was trying to find the razor's edge of parsimony, but it's actually kind of tricky to do so. And because there's sufficient conditions, this may not actually be a failure of the role. The role transposition may not be a failure of GDS in general. It just fails the way in which we can generate those sufficient conditions for selecting from the admissible action set. Well, the necessary conditions, just to answer the question from Chris in the channel, it's not so much about necessary conditions. So the necessary conditions here aren't fully articulated. So we don't actually know what is a necessary condition to ensure that if that was failing, we wouldn't have a GDS right from the beginning. All we have are sufficiency conditions. And so the question of whether there are properties that are lost from necessary conditions or whether there are additional restrictions that must be in play for those necessary conditions, it's probably going to work the other way. There are probably just other conditions that will allow us to, let's say, lift the dimensionality from a lower dimensional system to a higher dimensional system. And by unrolling into the higher dimensions, we recover this separation. So it would be kind of like if you have to work in the one-dimensional state space, then you have to confound F and G in the modified crosswalk. If, however, you have a state that's dependent upon the location on the line and something else, I don't know actually what it might be, we could speculate, and then have two dimensions, perhaps then a necessary condition can afford itself to say, okay, this is what is needed in order to get a GDS representation in this higher dimensional space. So my feeling is you have to lift to a higher dimension, but it's speculation at this point. Okay, well, just to give you kind of the wrap-up slide here, and we have time for discussion as well. Just things to consider, where we're going to go next and how we're moving. One thing to consider is when you design a mechanism that actually influences the state updates, the choice of the interface to the external world strongly influences the reachability of the system. So of course, depending upon, just as David was mentioning, if you actually expand how individuals can impact the state transition by adding, let's say, their ability to choose or to select different actions, that has a strong influence on where the system can go. And in particular, or rather in concert with, there's also the question of, well, how do you start the system? Is it sensitive to where you begin, where you can end up? If you have a system such that with varying probabilities, every part of the state space is reachable, well, that's fine. But if you have a system which is sufficiently complex that although anything can be reachable, some are significantly more likely, such that you reach a basin of attraction and you're always there, then the question is, well, how big is the set of initial conditions? If I start the system from anywhere and always end up there, it's a global attractor in that location, that's like an equilibrium that we would say is the equilibrium. But if we have a scattering of different initial conditions, that's important because number one, it happens quite a lot for complex systems. And number two, as designers of mechanisms, when people come to us as stakeholders or clients and say, hey, I want the system to do this, well, what we're really doing is we're setting up the way that the functions themselves are built and composed, number one. And number two, often just as important, trying to figure out where to start the system from. And so this will be the lead into to what we do in next week's final lecture of these three on the usefulness of the admissible action set as a lever, to get back to this idea of controlling, where you set the initial conditions and then you say, okay, conditional upon these initial conditions being the ones that we can choose as designers, we then find a high likelihood of arriving in this part of the state space. So we don't reach that first level of equilibrium except only in degenerate cases where it's globally asymptotically stable, for example, or globally stable. But we could say, given these initial conditions, we kind of map out where we're going. And that's super important from a design point of view, because what we would really like to do, for example, in like in an AMM, we want to make sure that we design the AMM such that we never reach part of the state space where the pool is drained, for example. So there would be a case of not enforcing certain initial conditions to exist, but rather selecting and then removing those initial conditions which lead you off into disaster. Okay. Question from Chris, is there something that can be developed in the context of GDS to a rank condition in an LTI system? Yes. So that's something that can be done. It is something that I think Zargham actually has an earlier paper on when he was applying the GDS framework formally to the Bitcoin network. And I'll try to dig up the reference for that, unless you've seen it already. It's either from 2017 or 2018. Okay. Any other questions?
Going back a slide to the
Sure.
just that first bullet point.
Yeah.
Yeah, just thinking about this. So are you saying that this is only for certain types of systems that it breaks the GDS framework, or is it that you need to design your mechanism such that it obeys this separation?
That's a good question. That's a good point. I should underscore that this is really, I think, more primitive than, or let's say more fundamental than the mechanism choice, where you would be, in a sense, saying, okay, I can make sure it doesn't happen as long as I design the mechanisms properly. Mm-hmm. With these sufficient conditions failing, the modification that we made in the crosswalk example was really just about adding a type of individual that is outside of our control. And so it's more or less the system that says, hey, there's this complexity here that's happening, this endogenous role selection. And if you were just to naively apply the GDS representation without understanding that particular type of endogeneity, then the conclusion that you would have would break.
Okay.
But it's good point, because as you said, it is like what we want to do is the second thing, like you're saying, we want to be able to say, well, okay, we know the necessary conditions. Let's lift it to, say, a higher dimensional surface. Now we design our mechanism so it doesn't matter.
Mm-hmm. Yeah. Yeah, and almost all our applications, well, like in kind of like going back to like how we would first try to attack these systems when they were so immature that really just had kind of like, clients that would come to us with a set of roles, and then, but there was no enforceability about, like, as you mentioned, like they can take on multiple roles. There's nothing in the admissible that we can make those things inadmissible anyway in a blockchain framework anyway, that they could take on multiple roles. So it's unenforceable. And that still fits with the crosswalk example too, right? Like a driver is also going to be a pedestrian at some point, and could also work for the city, and could also be deciding on the policy.
Very true, right? You could have the chairman of the group making the decision, who's an avid gamer, and wow, look, the crosswalk is right across the street from his home to the gaming
right.
Yeah, sure, you're right, and that is a big issue, because it's in a way, when you reach this sort of complexity threshold, which, as we've seen from the crosswalk example, isn't too high, you have to kind of use other tools to sort of assess the incentive compatibility of the different roles. And like we've seen in the graph, right, we've had to there's an individual, and they can wear all these different hats. They can be a curator and signal whether a subgraph is great. They could be a developer of the subgraph who can signal themselves. So they can also be a curator. Then they can actually just open up and be an indexer, indexing their own subgraph. And each one of the payoff incentives was designed essentially with these roles in isolation of each other.
Mm-hmm. Yeah.
So attempting to kind of build the incentive mechanisms where people can wear many different hats and can kind of choose, even unconsciously. And the driver isn't thinking, I'm now a pedestrian. The driver is just thinking, I'm jumping in the store, literally. And to try to articulate that within the GDS framework, I think is, I think it's going to eventually be necessary for us to kind of figure out how to make that a formalization. And then in the meantime, at least we'll move over and grab, incentive compatibility as our way of kind of like saying, well, there's a hidden type, and we don't know whether that hidden type is today a pedestrian, tomorrow a driver, or today a curator, tomorrow an indexer, but conditional upon that type, we want to at least design the incentives so that they don't break the system, for example. Yeah.
I think then you also get, like one of the themes that we usually talk about is like revealing your preferences through your actions. Yeah. And like in those, like in that set of kind of that you have this mixed, that agent with this mixed role, and do they maybe they vote against the crosswalk as like they're on a city council, but it's for their purposes as another role, as like the store owner down the street or whatever, and they want it there, like
that's a great point, actually, because that actually ties back into, that's nice. That ability to kind of try to think about how the admissible action set can provide us with revealed preference, is maybe the next lightest constraint we could place upon the system. So for those of you who haven't seen revealed preference before, this was an alternative way of specifying the outcome of an economic equilibrium, buying in a store, for example, that Paul Samuelson came up with it initially, that was saying, instead of looking at utility functions and saying what the utility is and the disutility is formally, let's look at all of the restrictions on the universe of prices and outcomes that can happen when all we do is watch what people do and ensure that they aren't doing something that's in a way irrational. And so he had a separate axioms of revealed preferences, they're called, which tell you whether or not, given a decision at a certain set of prices, for example, that's inconsistent with another decision the same individual made at a different set of prices. And as long as they're consistent, then you can say it satisfies an axiom of revealed preference. If there's an inconsistency, you would say this cannot be a representation. And then there was a huge amount of work to get what utility functions will match revealed preference theory and vice versa. But revealed preference theory is weaker. So in a way, it sits nicely in between this admissible action on the one side and then full behavioral assumptions on the other. And we could have a second observer jotting down and just watching what people do and then going back and seeing whether or not the combinations are rational or irrational. So I guess it's a really nice idea.
That's really interesting. I didn't, of course, you knew all the references that I didn't, but it's almost like economic, like system identification in a way, is what it sounds like.
That's exactly. I think that's a great way to look at it. It's a great engineer's way to look at this, because I don't think an economist would do that. Yeah, and it's actually nice because you can expand the crosswalk problem yet again to have two stores. And then if you assume that people are kind of indifferent between two game stores on the same street, but they have a weak preference toward one of them because they happen to be closer to their home, you can almost map some of the discussion that we've had today directly onto the hoteling linear model. Hoteling linear model kind of has the question of, was essentially retrospectively being used to answer the questions of why do we see gas stations on the corners next to each other? Why do fast food joints all agglomerate in one location? Why is it that that TGI Fridays is always next to Chili's? These types of condensations is explained with some so let's say some jiggling around by this idea that you want to choose as best you can a location that minimizes the chance you lose market share from people who have ideal points on a line of different product offerings that they have. And so I think that might be a nice way to kind of say, well, from a revealed preference point of view, we could start to entertain more complex methods. But as you've already pointed out, the things that we don't know are really difficult at that point, because if you don't know that there's somebody who is working for the city's spraying company and owns the paint that is actually used in crosswalks and wants to maximize the number of crosswalks irrespective of their utility, not having that information can actually harm the ability of this system to do anything with behavioral predictions. But it is nice to know that the admissible action set is always the same.
Yeah.
So at least being able to say what the reachable states are gives some power. And then arguably, to a certain extent, GDS is kind of robust to these things that could destroy equilibria concepts that rely very heavily upon knowing all of the information that the world has to offer.
Yeah, very cool. Thank you, Jamsheed.
Sure.
Yeah, I have a few things to read.
I'll try to put together I'll put together Samuelson's revealed preference paper as well.
Yeah,
it's very readable. I'll make sure to get Zargham's earlier paper on the blockchain GDS representation before it was GDS. So it's a version of it is GDS because that's what he came up with, but it's encapsulated really within the blockchain environment. Cool.
So along similar lines to sort of the departure from the expected or departure from the ideal, however you want to call it, is this system useful in a fraud detection scenario? So can you use it to identify actors that are sort of bending the rules in some way or another, or is it sort of blind to that?
So one of the areas that in fact that Barlin and Jesse and I have been looking at for the graph has been on examining these type 1 versus type 2 errors, where you have somebody who's engaging in fraud and what's the probability that you catch them versus the probability that you punish someone who's actually just minding their own business and just had a run of bad luck or just looked bad or had bad behavior. And all of those kinds of detections will rely upon being able to disentangle ex post selections from within the admissible action set. that lead to certain reachable states. So from the point of view of classifying the outputs, so the outcomes of the environments, the detection algorithm would only be allowed to look at the things that actually occur, that are observable. But then the inference has to then be made on what has occurred that would lead to that occurrence, to lead to that particular reachable state. And I think that for Gitcoin, I think that the algorithm for detection that Danilo and others had created, I think does something similar along those lines, looking at what the reachable state is and says, well, that's really unlikely to have occurred from honest behavior, but it is incrementally more likely to have occurred from bad behavior. And so by being able to parse out the trajectories, the reachable states into their likelihoods of coming from certain decisions, you could then use this, taking it one step back, to say that, well, we're not so much looking at choosing between different reachable states. We're saying there's one reachable location that actually happened, and we're inverting the mapping, so to speak, to find out where inside the admissible action set do we think people actually chose. So that's actually a nice, I think that might be a nice way, but I don't want to put words in Danilo's mouth or anybody else's who was working on the Gitcoin fraud detection, but I think that's the way you could do this. You could leverage the invertibility, provided that there is sufficient invertibility that you can get to a fairly high degree of confidence that bad behavior caused, or perhaps was highly correlated with, or from a statistical point of view, Granger caused, so that you actually change the probability distribution of the reachable state on the basis of the change that might occur in the admissible action set. I don't know if Danilo is, oh yeah, you're here. Yeah, so Danilo, was that a reasonable expression of kind of how the Gitcoin fraud detection worked?
Yeah, I'm thinking here. I don't have a good mental map right now.
No worries. It's more about kind of the idea that we can take observation and then through perhaps machine learning, just classify whether or not we think fraud has occurred or not with a 1 or a 0, for example. Yeah, but doing so within the admissible action set.
Yes, it's because, I mean, on Gitcoin, a critical piece is about the... Yes, I really don't... Because a critical piece is really, let's say, the idea that we also, let's say, include humans on the loop. So,
yeah, right.
In a certain sense, we do use the humans to, let's say, to define the reachability set. So, use them to map the territory. And in that case, the machine learning algorithm simply tries to, simply tries to reproduce those maps.
That's nice, right? Because it means that what really matters here is sampling between many different G functions, or sampling from the way the G function operates given the type of an agent. So if you say to people, okay, now you guys simulate bad behavior, and then that way gives us labeling points or features that we can label then for the machine learning algorithm to work on. That's actually selecting this G function that is done choosing different regions of the admissible action set. That could work. Yeah.
Yes.
I don't know if that answers your question, David, on kind of what you were thinking or how you were.
Yeah, no, that was, you know, the question was mostly around sort of what tactic would you take to sort of invert the goal. So yeah, that's good. Thank you.
Yeah, I think the invertibility from a probabilistic sense may actually be easier than invertibility of a mapping, because you may end up, I'm using invertibility loosely. I'm using, basically, I'm thinking of Bayes' rule instead. So instead you would say the outcome is conditional upon the action. So let's call that then, let's look and see then what was the probability of the action conditional upon the outcome. And that sort of thing as invertibility would allow you statistically to classify whether or not something is likely to have been caused by bad behavior. Yeah, in fact, that's also getting back to the graph. That's kind of where we are for the work that we've been looking on, this idea that you don't want to penalize people who have just had bad luck. They had a bug in their program and they did things that look really suspicious. But at the same time, you don't want to simply let anybody who has actually done bad things kind of just walk away or get away scot-free. So you want to make sure that these two different types of errors, as they're called, type 1s and type 2s, false positives and false negatives, that you try to drive those down to as low as possible.
Yeah, I think that one difficulty that I have with having the mental map is that, for example, on Gitcoin, we do not encode the temporal dependency explicitly. The sense that, let's say, the way that, I mean, it is somewhat implicit in the sense that, for example, we do several rounds for collecting more labels through humans. And there is a sequence in the sense that, let's say, on the second round, we have all the data on the first round plus the second. On the third round, we have all the data on the first and second round plus the third. Yeah. So, but besides that, there isn't a time error. So I think that maybe this is one of the challenges doing that mental map.
Gotcha.
And to be fair, it's one thing that we did consider exploring before, let's say as a feature or something that we could use as for collision detection, but yeah, I think this is a critical piece to, let's say, to make a mental map.
Yeah, thanks. I mean, it helps a lot actually also to ensure that we're doing time correctly, and also the information set that is available to condition on. I think it actually calls back to one of Chris's earlier questions about, how do you have a sequential equilibrium when you place the crosswalk down? And the idea here is that you're repeating the game by wiping out the crosswalk each period and then repeating it. So it's a simple repeated game environment where there's no permanence to the decision of the crosswalk. It's like a movable crosswalk. But that calls into question, if you had a history of where the crosswalk was, how much inertia does that bring into the system when you're actually choosing a decision on the basis of what individuals have done before? And so that temporal aspect, I think, is super important also because of the non-Markovian nature that it can introduce, and therefore it can cause interesting issues if you're trying to estimate something on the basis of something which is actually history dependent, because then you've got that dependence that you don't know about or you've discarded in the model that you've created. So richer game theory models will allow histories, but yeah.
Yeah, another type of timing that we could also think about is also timing as measured by causation relationships, in the sense that, let's say, each cause-effect relationship could be a step on timing.
So you would complete then the cause and effect into one node, let's say, and that would be the unit of time moving forward, or the event that would be used.
Yes, because, for example, on Gitcoin case, we do not encode the temporal dimension explicitly, but if we think that, let's say, round 1 causes round 2, which causes round 3, perhaps this is something that we could, let's say, associate with a time dimension. Nice. But it's really, let's say, a free topic, because I've been reading a bit lately about causal inference, and perhaps this could be a topic for a RD meeting, but.
Cool. Yeah, nice. Okay, other questions? Unfortunately, I have to drop off now, so if I just entertain one quick question before I have to go. Okay, I will make sure to get the copy of the slides to you guys in the channel as fast as I can, as well as those references that were mentioned for Samuelson and also for Zargham's earlier work. So in any event, thanks everybody for the comments, especially, and for listening, and then look forward to next week's conclusion. So thank you.
Thanks a lot, Jamsheed.
Thank you.
Thank you.
Thanks, everybody.
Great presentation. Thanks so much.
Thanks.
Catch you next week.
Yep.